you doing, everybody? Randy Richard in the shop, and this is part 2 to the motor overhaul, and we'll get right into the commutator. Sorry I had to split this into 2 pieces, just too much internet troubles here locally with new cabling they're putting in the ground, fiber optic stuff and phone lines and all that stuff. It's kind of been tough the last month or so. Be sure to check out part 1 of this so you can see where we're at with the motor. We'll be wrapping up the table saw soon with the motor. Once that motor's on here, not too much else to do. So do the electrical and get the saw set up and cut something. So we're almost there. So thank you guys for sticking with me, and enjoy the video. This is the armature of the motor. This part here is called the commutator. And probably just about everyone who's ever fooled with any kind of motors, you've seen a commutator somewhere along the line. Many types of motors have commutators. Of course, a lot of modern motors today don't, but any older motors you're probably going to see one because there's many types. But anyway, what they are is a wound rotor where they have actual windings in the rotor, and each one of these bars is connected to one of these sets of wires you see here, and between their segments and between the segments is an insulator, and that insulator is made of mica. It's extremely good insulator. It can be very thin and still have extremely good dielectric properties, insulative properties. But how this works, and the brushes ride on here. So, here's a brush, and the brush rides on here like so. You don't want the mica to be higher than the commutator bars. You want it to be, and you really don't want them to be even flush with the commutator bars. You want them below the commutator bars. On the commutator, this looks very smooth, and it is. And you do not want, for the commutator to work properly, you do not want the mica to be flush or above the commutator bars. Now, this is flush, and we want to take some of the mica out and lower it so that it is below. So it's called undercutting. Now, undercutting is really not that hard to do, and you can do it with some very simple tools. Old hacksaw blade. I just ground it on the grinder so it has a sharp edge in here, a sharp point. It's just the right width for this sort of work. It makes one of the very great tools for cutting down the mica. They make a machine that will do this, but you're not going to own one, are you? This is a hacksaw blade with the teeth on it still, and just kind of curved back out of the way, so I have a very nice tooth on the end, and for doing the initial cutting and getting it down. How deep do you want to do this? You want to do it about 3/64 of an inch, which is 47 thousandths. Now, if it's 40 thousandths, it's okay. I've done this quite a few times on motors when I worked on the ship and such, and you can just judge it by your eye. It's very hard to measure unless you have a micrometer with a real thin blade to reach down in there. But there's more important issues about the depth. Other than the depth, I should say. You don't want the mica to ride up on the sides. So you either want it to be, a V groove is fine, but you've got to get it off the sides so that mica doesn't ride up the sides, and you want to see that when you're undercutting. Now I'm going to show you some of it. I've already undercut, and I'm going to show you what it looks like, kind of. Now it's kind of scratched up, but we're going to fix that too. So here, this is going to be very hard to see, but here, these are undercut right here. And you'll see that there's copper on the sidewall. And that's how you know when you get rid of all the mica on the side. And you can just take this tool and scrape that down like that at an angle. And you just do it on each side. Now mica's fairly hard, so it dulls your tools and you might have to regrind and such. But you use this tool I use this tool to start the cut and get it going. So I'm not quite halfway around here. I'm going to hold my hand here and try to shade this a little bit so you can see these undercut ones here. Yeah, this is very hard to tell, hard to show. Anyway, I use this tool here to start my cut out here on the end. Get it kind of started gently and work your way up it. All the way to the end. You want to stay between the two bars. Now I like using like an old toothbrush to brush that out, keep it clean so I can see what's going on. And I see black along the edge. I don't see copper. And so what I have to do is scrape that like this on the edge. I don't have a very good camera for this up close type of shot, but I think you kind of get the point here. Now on this commutator there's 56 bars, so I have a lot of grooves to cut. This will easily take you a couple hours maybe to do with this commutator like this. So after we get that all cleaned out, I mean we get all this done and you see it's all kind of scratched because you slip or whatever. You want to give this a little sanding and clean up. Now we take our little wooden block we made that just fits the commutator. Okay? Just fits. Just right. And we put on some paper. Now, the type of paper is very important what you use. Do not use emery. Do not use garnet. Use only flint paper. Flint isn't so hard that it can embed in the copper. And all the other ones, this is the only stuff you should use, is flint paper. Maybe a little harder to find, but it's fairly of a soft abrasive and it will not embed. And it's the only recommended type of paper to use on commutators. Now I made this block up and I put a screw in here to hold the one side. Boom, boom. And you can just sit here and just rotate it and buff this out. Now if you had high mica, or you eroded a lot of copper for some reason, the mica is actually sticking up, which can happen, you want to do this here to sand it on down. Or you're going to put it in a lathe and take a cut on it. This commutator has already had a cut taken on it and over its lifetime. I don't know, right here is a step, and that's where the original commutator used to be when it was new. You'll usually always find a step that when it's first machined, and then it obviously has this other step, so it's been machined at least one other time down to where it's at now. So I really didn't want to machine this again, and it didn't have high mica, and it didn't have bad eroding from sparks. So I've opted for this, and the brush is right from here to about here, and this last little part, there's not hardly anything. So it hasn't had a lot of use since the motor was worked on one time. It's starting to clean up pretty good. Now I'll do this when I'm all finished and get this really sanded down. And I just wanted to show you what I'm doing and how this is all going to clean up. You'll see it when I go to put it all together, the motor and everything. After undercutting everything, it's pretty worn as far as there must have been a lot of arcing going on, and it's just not enough to really sand out. So I put it in a lathe and I checked it. The shaft is straight, run out is less than a half a thousandths, but this has a run out of about 5-6 thousandths. So I might as well just put it in here, and I'm going to take a real light cut and clean up the commutator. Then I'll have to go back and scrape all the edges and get all the burrs off and all that. There, well, at least it's round now, and a little bit smoother finish, and so we're just going to sand that a little bit, and then we'll go back and scrape all these edges so they're nice little chamfer on them. We'll just hand scrape them and clean up all these burred edges. And I got rid of the shoulder that they had left from the turning before and cleaned it up. But it's round now, or true and concentric to the shaft, which is really good. Otherwise your brushes are going like this all the time. I just used my little hook tool to bevel or chamfer, I should say, each edge of all the of every bar along here, and a little more scraping on the insides just to make sure everything's right and good depth. There's a few, and then just went around it with the sandpaper block to clean up anything else that might come off, and it looks pretty darn good. It's round at least, and clean and smooth. So, and we got rid of all the burrs, and I think she's ready to go. And a little Another vacuum on there and brushing. So get a little more dust out. She's good to go. This is a great book. Just a paperback. And if you were going to have a motor book in your shop for just general maintenance and how they generally work and all that stuff, this is an excellent small book. It's I've had this since college, basically. And yeah, look at that. My name in it. And so we can just go right here too. Here, what was this here? Copyright 1960. So especially covering all sorts of motors, all motors just about. Let's see here. Basic principle, motor protection devices, control devices, windings, universal motor, three-phase motors, capacitor motors, split phase, repulsion, shaded pole, motor testing, and enclosures and mounting characteristics. You know, some of it may be outdated, but tell you what, excellent little book. Especially if you want to understand some of the stuff I just did about the commutator. Here's commutator care. Here, it starts way back here. Commutator care tells you about checking brush and concentricity, which I did on the lathe. Setting up the armature in the lathe, cutting tools, grinding it, stoning it, the wood block method with the sandpaper right there. About high mica, about slotting files, and using hacksaw blades. Right there. There's your tools. Oops. Here we go. Here's your hacksaw blade tools. You know. Oops. I don't know where the other one is. Anyway. About how to cut your mica, about watching out for the side mica fins on the sides, things like that. You know, a slight edge on there is okay, but so just so it's not a rough edge. Anyway, great little book. Tells you about repulsion motors, repulsion induction motor, and that's what we have here. About the brushes. About your shorting ring. There's a shorting ring right there. How to set it up at 17 degrees or so to plus a little bit more maybe. It's kind of vague on that, but you start at 17 degrees with offset on your brushes. But how it works and all that good stuff. So excellent little book to give you an idea how these things, how all these motors work, and so you can do this work is not that hard to do if you want to do this yourself, fix up your motors. So this is a repulsion induction motor, and it has a wound rotor with a commutator, and what this does is the commutator and the windings are only in action when the motor starts. All the electrical current comes into the field, the stator, and then there is induced voltage and current formed in the rotor, and then it's short-circuited across with the brushes, with the brush rigging. There's two sets of brushes, and that helps the motor start. It gives you the offset. These are 17 degrees offset, so those poles are set up, and it gives it a rotation. That's what it does. Anyway, so the motor starts to turn, and the brushes stay in play with this alternating field build up and collapse every set of bars it crosses over, every pair. Then you have the shorting ring, and as you get up in speed to about 80% of the speed, now this is a 1725 motor, so when you get up to about 80% of that, this is mounted right here. These copper bars, these are just in here with a spring holding them, and they'll flip out. do the centripetal force, right? They're thrown out like little flyweights, right? And what they do is, this is up there tight, but they don't contact anything. But when they get thrown out, they make contact up in here. Now this is rotating with the motor. It's on here snug, and it rotates with the motor, with the rotor. So they get thrown out, and they short this whole thing out. This all gets shorted out. So now there's no current flowing anymore. The brushes aren't doing anything, and it becomes an induction motor. So it uses the repulsive force to start, and then it takes over. This gets kicked out. There's no more repulsive force, and in running mode, when this shorts, and it becomes an induction motor. Under here, you can't see. It's just like a squirrel cage induction motor today, where there's aluminum bars through the rotor, underneath all the windings, and that's the induction part of it. It works just like a regular single phase, 3-phase squirrel cage induction motor. Then once it's up and running, but it uses the repulsion force with the commutator and the shorting mechanism to induce a field in the rotor to get it started and get it up to speed. Now typically these motors have actually really good starting torque because of this extra help in starting. But on a table saw joiner, you don't really need a lot of starting torque, but this is the motor that is on here. So we're going to put this back on. Now I cleaned all this up, so it makes good contact and everything, and then this gets on there. It rotates with everything, but it's not like super tight on there. Now there's this big snap ring that we got to get back in place in here. Okay, I got the shorting ring installed. This snap ring thing is round, and it was a bear to get in. Fortunately, my son stopped by and just at the right time, and he helped me get this on there. I don't have a pair of pliers that hold that sort of thing to open it. And a little bit of bear, but we got it on. I'm just going to knock this on. It's not that tight of a fit. Both bearings are the same size. This is the motor stator cleaned up. Now what I did there with the new lead, so there's the new leads all secured, and nice long rubber grommet, that piece of hose actually in there to really protect this well from flexing and protect it from the sharp edges. Doing it this way works really good if it will fit inside your box. So the leads are all ready to go. Get it as straight as possible. Now down in the bearing housing, go this felt ring, this washer, and a spring washer pack sits down in there. Now originally this is a dust seal. They might have oiled this or something originally. Maybe I'll just rub some oil in it. The bearings are sealed. All it is going to do is help keep dirt and dust out. Instead of oil, I'm just going to rub it with some grease, so it's just kind of damp, so it has something that won't get hard. The old ones were rock hard, so That way it'll stick in there. Now we're going to slip the rotor in there. Like that. On this end we'll have another, no spring washer, just a felt and a washer will go on there. We'll just slip those in the housing. Alright, this is the brush rig right here. They're falling out. I'm not going to put the springs on yet because it just makes it harder to get it all in there. That way they'll stay back. This one's to this one it goes to this one. Now, there's a ring in here, and of course it's loose, right? So we have these special little screw type things go in here. They're threaded on the inside, and a screw will hold it from the outside, and that little notch hooks into those little notches so they don't turn. It's a pretty nice little rig. So we're just going to put that in there. So we can also, we'll be able to try to adjust this. So I slipped in here's the felt and the washer. And this goes down in here with these little doohickeys. They slip into the holes. Alright, that's set in there, and this way we'll be able to adjust this to the right angle. Through bolts, they got a little insulator like tube that goes on them. They're kind of a paper thing. So we'll slip those on and fish those through. And we got acorn nuts. I got some brand new acorn nuts, stainless ones to put on, so being kind of nice. Okay, got all the through bolts in and nuts on and tight. Now don't be superhuman tight on these. Just make sure they're solid. Just, you don't have to. You can break those, but they're only 1/4 inch bolts, basically. So you just want them good and just snug. They don't have to be real tight. Just holding enough to hold it together. And look, it spins perfect. And I just reaching in here, flipping the springs off so that the brushes are against the commutator. I still got these bottom ones to do. Now I have this loose, so I can spin this around and make sure the brushes are down and put the spring on. There. Now all the brushes are seated. Alright, I'm going to use this to set the angle of 17 degrees on the brushes. Now I put it on the table and zeroed it out. Oops. Well, I did. Anyway, I'm holding it right in line with, I can see the brush right in through this slot here. Horizontal is neutral, and then 17 degrees up from neutral. So I'm going to hold this at 17 degrees, and and I'm right in line, it looks like, with the brush, right in the center line of the brush, and it's close enough. This doesn't have to be absolutely perfect. If it's 17 or a little above 17, great. If it's a little below, it will work. They say it's a little more than 17 is the perfect angle for max starting torque. And then we'll just snug these up. And we'll see how it runs. So right here, under the principles of repulsion motors, field windings are series. Field windings are series connected to the line input. But you'll see here, this is 17 degrees. Your neutral angle, horizontal with the poles, and then off 17 degrees. And that's where I set them. Now I said this was an approximation because here what they say is better commutation and longer life are possible if the angle is made slightly greater than 17. So 17 is like the most perfect angle in theory, and if you go a little bit more, it's okay, and or if it's leaving a little bit less, it's okay. We'll see how it goes. If we're giving too much sparking and stuff, we'll probably increase the angle to maybe like 17 and a half or 18 degrees and see how that goes. I failed to film the seating of the brushes, but it's not a big deal. So I just reused the same brushes. They were already in pretty good shape, so it wasn't much. But I failed to film it, so we'll put the cover on here. We have our electrical box. I think I'm going to put it this way with the cord that way, but I never know. I might end up flipping it over. We'll see how it goes when it's all mounted. There we go. This reminds me of Superman colors. I have a cover that I made. It's aluminum. It's buffed out, polished, but I'm going to engrave something on the front, I think. I just haven't done the engraving yet. And the all-important badge. This is the original badge. Delta. Ball bearings, 1 horsepower repulsion induction motor. Model R5074. Dual voltage, 110, 220, 1725 RPM, 60 cycles. Draws 13 amps or 6.5 amps. 40 degree continuous. Delta Manufacturing Company, Milwaukee, Wisconsin. And the best of all, made in the United States of America. Thus the colors, if you didn't figure that out. Alright, the motor's ready to mount. Came out great so far, and we'll test run it here next. I've got it wired for 110, and let's see how it goes. Okay. And to give it a little help. So we'll need to, there we go, finally got up to speed. So we need to adjust that angle a little bit. I shouldn't have to help it. The angle on the brushes, we'll increase them a little bit. Alright, increase the angle just by eye. Let's see what happens. Okay, didn't have to help it. Start it up. Sounds good. Running smooth as can be. Put try a little more angle, just a little bit. There we go. Starts much faster, much better. Comes right up to speed. That's how it ought to be, not that slow start. So that really jumped up. So we'll try just a little more angle. Okay. Increase the angle a tiny bit more. Notice that? Boom, starts right up. I think we'll just leave it there for now. And we'll see how it goes when we put it on the saw and see how she works and cuts and all that good stuff. This is awesome. There's no sparking in there at all, so that's really nice. The brushes are running really good. We'll put it on the saw, and once we get her hooked up and everything, we'll see how we go. And we can always adjust this a little bit on the saw if we have to.